Okay, well, good morning, everyone, and welcome to today's Fireside Chat with IperionX's founder and CEO, Tasso Arima. I'm James West. I run the Sustainable Technologies and Clean Energy team for Evercore ISI. IperionX is the leading developer of low-carbon titanium for advanced industries, including space, aerospace, electric vehicles, 3D printing, among others. The company controls breakthrough titanium technologies that produce products that are low carbon and fully circular. Currently, the company is producing titanium metals powders from recycled titanium scrap at its operational pilot facility in Utah, and it plans to expand its production capabilities at a titanium demonstration facility in Virginia. The company also owns a 100% stake in the Titan project, a critical minerals project with the largest JORC resource of titanium, rare earth, and zircon-rich mineral sands in the U.S. By leveraging its advanced technologies and strategic mineral assets, the company is poised to revolutionize, we think, the titanium industry and become a leader in sustainable materials production. Tasso is a highly accomplished resource executive based in the United States with a remarkable track record of identifying company-making resource projects in North America and Europe. He currently holds the position of managing director and CEO at IperionX, a leading minerals technology company that is dedicated to establishing low-cost, low-carbon titanium supply chain that is entirely American. His prior experience includes his role as the founder of Piedmont Lithium, where he played a critical role in securing the funding that enabled the company to grow into one of the most important lithium chemical projects in the United States, ultimately resulting in its listing on the Nasdaq Stock Exchange. Born in Greece, Tasso is immigrated to Perth, Western Australia, where he earned a Bachelor of Commerce and was working towards a Bachelor of Engineering from the University of Western Australia. So, Tasso, thanks for joining me today.
Yeah, appreciate that, James. Thanks for having me online.
Of course, yeah. So I think what the initial plan was you guys released a major study on hydrogen electrolyzers and the titanium needs in hydrogen electrolyzers, and I think we were going to go through a few of the slides there so we can kind of lay the groundwork on what you're seeing and where we could run into major supply chain issues.
Yeah, absolutely, James. So I've just prepared something here that I'll take us through, which is a quick background of our company, and then how we intersect with the hydrogen economy, especially the green hydrogen economy, and how recent legislation like the IRA, we believe, is going to push the demand for green hydrogen and eventually push something that a lot of people don't understand, which is the supply chain for titanium into the green hydrogen economy. So I'll take us through that, and then we can go through whatever you want on some questions. Just as a bit of a background, you mentioned it. I grew up for the audience. I grew up in Western Australia, but I'm Greek born. I then actually dropped out of university, did get my Bachelor of Commerce later to get my visa into the United States, but I was the founder of a few coal companies in the fossil fuel energy sector early on in my career, which were very successful. One which we took to over $1 billion, which is in production today, one of the largest thermal coal mines in North America. And then I moved to the United States in 2015. I live in Florida today, but I travel around the country a lot. And I founded in 2016 Piedmont Lithium, which Evercore knows extremely well. You all banked us in the last few years. Did it extremely well there, building a supply chain. Really focused in 2016 on building a supply chain for what we could see was coming, was the electric vehicle revolution. And we were correct in that investment thesis. And importantly, we built an excellent team in my organization of identifying and looking at those supply chains that are missing in the United States. So as a background to start in titanium, we were really focused on some issues that we could see coming up in titanium, which I'll take us through, which is mainly that it's refining of titanium metal, like a lot of other critical minerals needed for energy transition, has been offshored. Right. And so we looked at reshoring the titanium supply chain, but doing it sustainably with a new process that I'll take us through, and doing it for lower costs so that we can expand the role of titanium use across industries. And then as we've seen over the last 6 months from industry approaching us, both PEM electrolyzer manufacturers and end industry, we see a huge opportunity to parlay our sustainable titanium metal into what is going to be a huge supply shortfall for Western titanium metal into the green hydrogen economy. So with that, I'll probably take us through and start here on this. And I think we'll give a good primer to everyone and the audience that's watching as to what we're doing. So we are both NASDAQ and ASX listed, with primary listing is on ASX, it's dual listing on NASDAQ, very similar approach to what we took with Piedmont Lithium building this company. We started off as a private company. We then listed into a public shell on the Australian Securities Exchange in late 2020. And then last year we did a dual listing on the NASDAQ. In the future, we will aim to follow the same path as Piedmont Lithium and become fully domiciled here in the United States and be a primary listing on the NASDAQ. It's natural because all our employees and all senior management is in the United States. So the vision for us is sustainably reshoring the titanium metal supply chain and also making it cheaper so that we can disrupt stainless steel and aluminum. Everywhere where you see especially stainless steel use, you could have titanium metal use, but you have not, because titanium has been wildly more expensive. Now, the benefits of titanium as a primer for everyone, it's stronger than steel and aluminum, especially the titanium we manufacture is typically an alloy called Ti64, which is 6% vanadium, 4% aluminum, super strong, typically 3 to 4 times as strong as stainless steel, but it's 45% lighter. And then in addition to that, it's far more corrosion resistant. So if you were to put stainless steel in the ocean, it would corrode in maybe 5 years. You put titanium metal in the ocean, there's no data as to how long it corrodes. It will not corrode. Whereas low carbon steel, traditional steel will corrode in only a few months. So it's a superior metal that should be used in replacement, especially of stainless steel, but is not because of its cost. So we're looking to build this titanium supply chain, and how do we do it? We are looking to scale up our revolutionary technology, which allows for us to use 100% recycled content, which is a world first, but also allows for zero scope 1 and scope 2 emissions. So that revolutionary patented titanium metal technology was developed by Dr. Zach Fong at the University of Utah, funded by the Department of Energy. And we are taking that, we are producing powders in our industrial pilot facility today, and we're scaling it today. Now, over the longer term, we will eventually run out of scrap. There's a lot of scrap in the market today, which isn't fully recycled. We can bring that and make it fully circular. But in the future, as we continue to build our business, we will need minerals from the ground. And so we have the Titan project in Tennessee between Memphis and Nashville. It is JORC and SK 1300 compliant. It is the largest titanium mineral resource in North America today. And it's got a nice co-product of rare earth minerals and zircon. So looking to build that fully integrated supply chain over the long term. In the short term, build our recycling business first and backward integrate it over the longer term with our Titan project. So while we're focusing on titanium, biggest initial challenge that we wanted to solve back in 2019, 2020, when we started looking at titanium, was that global capacity had moved all overseas. So in 2019, the last titanium refining facility in the United States was announced that it would shut. And subsequently, it has shut. It shut in 2020. And you could see that all titanium refining, similar to a lot of other things, lithium, cobalt, the carbon anodes, rare earths, was all moving overseas, with the majority of it going towards China and Russia. 58%, I believe, China today controls, and that continues to increase, of the refining capacity of titanium metal. Huge issue, mainly not just for the commercial sector, where it's used extensively in aerospace and medical, but especially in the defense sector. F-35s through to our M777 howitzers, lightweight howitzers, 100 of them are in the Ukraine today, helping win the war, through to naval applications because of the corrosion resistance and its lightweight. A lot of titanium metal use across, and increasingly across, our defense platforms. It's a strategic need to have a non-Chinese, non-Russian supply, secure supply of titanium metal. Another big reason we focus on titanium metal is the potential for titanium metal, if you lower its cost, to be a substitute for stainless steel and aluminum, and some other materials as well. We announced a relationship with Canyon Bicycles, the largest direct-to-consumer bicycle manufacturer in Germany. LeBron James invested in them last year. We're going to be replacing some carbon fiber components with it. So a huge market opportunity here is we lower the cost of titanium metal, which we believe we can do with our process. And then the other big reason we focus on titanium metal is the sustainability. You need to improve the sustainability of the titanium supply chain. Today, titanium metal is one of the most carbon intensive metals in the world. And that's because of its process that I'll take us through on the next slide. And in addition to that, it has the potential to be infinitely recyclable, but it is not today because of the process. You both have not 100% scrap being able to be recycled, and you also have the process not being able to utilize 100% scrap. So there's a need to bring sustainability, both financial, economic, and environmental sustainability to the titanium supply chain. So why is this the case? The core issues around the titanium industry moving offshore, being expensive, and being unsustainable, it's less got to do with where the minerals are located. Titanium minerals are located in a vast across the globe, in the vast majority of countries across the globe. But the refining is where the issue is. This is very similar to the lithium supply chain today, where you have lithium across the world, but you have refining capacity that's centered around China, same as the rare earth supply chain as well. And why is that? Because the Kroll process today is a very carbon intensive, energy intensive process that also results in a lot of toxic or needs a lot of toxic processes involved in it. And so places like China and Russia, who have less focus on environmental regulations, were able to leapfrog ahead of Western worlds and develop these supply chains and continue to build them up based on this process. This process is very complex. You have to go through a carbon-intensive carbothermic chlorination process to create titanium tetrachloride. From there, you go through a complex molten magnesium metal reduction process, and then a distillation of that resultant magnesium chloride, which creates what's called titanium metal sponge, which is a coral-like appearance of titanium metal. You then need to melt that in a very complex melting process. Typically vacuum arc remelting is used, where you create a electrode and you melt that in a vacuum. That's where you can add in scrap, but you can't use 100% scrap in that process. And then you create these big ingots. Well, big ingots, you know, if you want to watch or you want a bipolar plate as an electrolyzer, well, it's not a big ingot. You have to get it there. You can't melt titanium in the open atmosphere like you can stainless steel or steel. So you have to then go through some complex extrusion processes. In the case of making spherical powder, which we produce today, you have to make wire, then gas atomize it. If you want to make plates, you have to extrude into plates. Very complex process. A lot of scrap generation in that process. That scrap is not 100%, not 100% of that scrap is recyclable. So you have a very complex, energy intensive, carbon intensive process. And so that's led to, you know, the issues around titanium metal, which we want to solve. So how do we solve it? We solve it because we have a complete revolution to the supply chain that we look like. Our technology, which is called the hammer technology, allows for directly taking scrap, 100% scrap today, and producing titanium metal powders, which can be used in additive manufacturing to make titanium metal products. In the case of hydrogen, we can make the porous transport layers, we can make the meshes, we can make the bipolar plates. This technology, which I can get into more detail in questions and answers, allows for us to use 100% recycled feedstock, but is also, when we use renewable power for our facilities, which we do today in Salt Lake City and will in our future facility in Virginia, allows for zero Scope 1 and Scope 2 emissions. And we're completing our life cycle assessment soon, which will show, which we believe will show some of the lowest carbon intensive metal production globally. So complete revolution to that complex supply chain, which allows for environmental and economic sustainability of the titanium metal supply chain. Today, we're doing this and we're producing powders day in, day out in our industrial pilot facility in Salt Lake City. We are already doing it on 100% scrap. We are already doing it with 0 Scope 1 and 0 Scope 2 emissions. So we're already achieving our sustainability objectives, even at the pilot, what we call an industrial pilot scale. Now, this facility is enough for us to produce powders to do some low volume production runs, where we've already secured some customers in the luxury goods sector, in the bike sector, but to also allow for us to do prototyping with customers across other industries like consumer electronics, like green hydrogen. Now, over this year, because of the immense interest we've had in our sustainable titanium metal production, over the last 12 months, we've been designing, and we secured a site in Halifax County, Virginia, where Governor Youngkin came, and we did a grand opening, essentially, of the site. And by the end of this year, we intend to be commissioning our new production facilities in South Boston, Halifax County, Virginia. This will take our production to 125 tons per annum, and we'll scale from there. Again, this would be the first of its kind, 100% recycled, 0 Scope 1 and Scope 2 emissions, fully ISO compliant, fully UL compliant for recycled content, and will really put us on the map in revolutionizing the titanium supply chain and allow for a commercial option for a lot of our customers, especially in the hydrogen market, which I'll get into now, for a non-Chinese source of titanium metal. So we've had a lot of interest with our customers. We've already secured key customers across luxury goods, across bikes and micromobility, where we see huge opportunities for low cost and sustainable titanium metal. Anywhere where it's touching the consumer, where they want sustainable products, but also titanium metal is a premium product, we're having a lot of headway. We're getting a lot of interest. We also have a lot of interest, of course, in defense. We won the US Air Force Research Labs Grand Challenge at the start of this year, where we're recycling titanium metal for the Air Force, for the US Air Force. We're working with one of the largest pump manufacturers for the US Navy. We're making big headway in all our target markets. We see a huge market in consumer electronics. But what we're talking about today is green hydrogen. This is a market which really we didn't know of until about 6 months ago, when the industry came to us. And this is a market where we see immense amount of titanium metal needs, and a lot of titanium metal needs, which today is currently being fulfilled by China for the green hydrogen economy. So just as a primer, before I get into the use of titanium metal in green hydrogen, and I believe you, James, and Evercore would have some really good data around here, but from the IEA, we see hydrogen, and especially green hydrogen, accelerating over the next decade immensely. We're starting from a base of very, very low for PEM, or alkaline hydrolysis. But we see over the next decade and over the next few decades that green hydrogen economy will grow substantially. Now, a big reason for it, well, of course, you have the sustainability aspect of it, moving towards net zero economies, moving towards more sustainable economies. Hydrogen is a big part of that. But a big shot in the arm for the green hydrogen economy has been the IRA here in the United States. Not only do you have that huge amount of funding coming from the IRA into energy security and fighting climate change, but you've got some significant incentives in the form of a production tax credit, which is actually enormous, $3 a kilo, and a capital cost tax incentive that I think is going to really give a shot in the arm and accelerate that green hydrogen economy, similar to some of the earlier funding that came from the government in the mid-2010s, which helped accelerate the EV revolution. I mean, if you look at it, that $3 a kilo production tax credit in places like Texas, where you have cheap solar power, that could end up in negative production cash costs. That is really going to absolutely drive the hydrogen economy. So we see huge growth in the hydrogen economy. So what does that mean for titanium? So what we've done here is we've shown similar to what I saw in the electric vehicle sector back in the 2016, 17, 18 timeframe. People used to show, what is in an electric vehicle battery. There's a lot of lithium, there's a lot of graphite, things people didn't know. I think people don't know, but there is a lot of titanium metal. In intensity, there's more titanium metal than there is anything else. People look at the PGMs, which rightly so, the iridium, the platinum, those metals are extremely important, but they're only a small fraction of the overall PEM, and we're talking about PEM electrolyzers here, only a small fraction of that. If you look at titanium, because of titanium's strength, but also its corrosion resistance, commercially pure titanium is used extensively across many of the parts of a PEM water electrolyzer stack. And I think there is this supply chain is being overlooked. And I think just like we saw the lithium supply chain get constrained and a lot of the other metals that are going into the battery supply chain get constrained over the last few years, I think if we don't look to bridge this gap, we're going to have issues with our titanium metal supply chain because it is a significant portion. It is the majority portion, or not the majority, a large portion of the PEM electrolyzer today, and something that I think people increasingly is going to be an issue for the electrolyzer manufacturers to secure. We've done some modeling looking at electrolyzers. If you look at average titanium sponge imports, which goes into melting, because we're import reliant today in the United States, you could see a situation very quickly where you exceed by a significant factor the need for titanium metal. And then when you take into account fuel cells, which we believe will grow once you have cheap hydrogen, fuel cell capacity for trucks, the marine industry, aerospace could grow immensely over the next few decades. If you take all that into account, you could see a situation where you've got more titanium metal need for just the hydrogen economy than what you have titanium production globally, let alone what we are importing into the United States today. And that is obviously an issue. This is similar to what you've seen it happen in the lithium supply chain, or what you see is happening in the rare earth supply chain. We, in our modeling, have seen the potential for huge titanium metal needs, which I believe a lot of industry is, because of the complexity of the titanium supply chain, does not understand that this could be or will be an issue in the future. One big issue that should stand out, though, let alone the growth and that supply chain gap, which we see coming, is the fact that today the capacity is concentrated around China. When you consider that the ex-Chinese supply chain is now, because of the Russia-Ukraine war, Russia was a major supplier of aerospace-grade titanium metal. Now it's moved all to Japan. When you consider that the ex-Chinese supply chain is focused on bridging that gap that has come up because of the Russia-Ukraine situation for aerospace titanium metal demand, it is really China which is there to fill the demand for the industrial applications, including hydrogen. This is a big issue, not only because it's China, but because today a lot of Chinese production, 20% of it, is going through the Xinjiang Autonomous Region. This is the region which is under the Uyghur Forced Labor Prevention Act. And it's going to mean that groups, whether it's a German or a US electrolyzer manufacturer, they're going to have to warrant or guarantee that, or somehow trace that it has not gone through some sort of forced labor. And so this just increases the complexity of sourcing for titanium metal in the electrolyzers in the future. Unfortunately, almost all roads lead through China in PEM electrolyzers today. And so what we're aiming to do is build a supply chain here in the United States, which not only is ex-China and offers a Western world source of supply and is quickly scalable, but one that is also more sustainable from a carbon intensity perspective, more sustainable and fully circular. So when electrolyzers reach their end of life after 7 to 10 years, we can recycle all that titanium metal, which is not possible today through the current industry. You're not going to take an electrolyzer apart, send it to China, the current process can't even recycle it anyway. You could have a fully circular integrated supply chain here. We see ourselves as the sort of redwood materials for the green hydrogen titanium components that go into the electrolyzers. We aim to revolutionize the supply chain. We aim to offer a alternative which is much more sustainable and ex-China, ex-Russia, and we aim to be a big part of the need for titanium metal in the future. But I think this is something that, as the green hydrogen economy grows, I think there's going to be a lot more focus on what we're doing. So that's a quick overview. I'll hand it back to you, James, for questions.
Well, sure. Maybe the first one from me, Tasso, as we think about the different types of electrolyzers that are in the market, the kind of the big three, if you will, is there a way to shift away from PEM electrolyzers into a different electrolyzer where I don't need the same amount of titanium?
So you could shift. I think there's obviously a lot of work's gone into PEM. It's sort of like saying, could you shift away from different types of lithium batteries? I think what you're going to have is you're naturally going to have a market which is split between a few different types. But what we've seen is that some of the large players out there have already committed to the PEM electrolyzer. And I think when you compare the supply chain, with us being in there, I don't think there's going to be an issue with titanium metal. We can scale and we can provide a circular supply chain for those titanium metal needs, which will significantly ease that supply chain issue that's looming there for the titanium metal. But from a shift away from PEM to other electrolyzers, other types of electrolysis, I just see that you've already had commitments by some of the major groups like Siemens, Cummins, Plug Power already in the PEM. You will have alkaline hydrolysis with take a chunk of market share, but I don't see it being all of a sudden a Siemens or a Plug Power will let go of PEM electrolysis. I just think what will happen, what we hope to happen, is that they'll look at the supply chain. People will engage and will try and fix that supply chain before it becomes an issue in the coming few years.
So how would you, I guess, you and I were talking about this a bit before we started the webinar, but how would you liken this to or compare this to the lithium supply chain as the challenges that we clearly saw 3, 4, 5 years ago, and the evolution of the market to where the OEMs are kind of controlling, some of the battery supply or investing in the battery supply, which some of the batteries are investing in the lithium suppliers. Is that a similar type of process you think will happen?
I think so. I think what the benefits here is that, having gone through the pandemic, people understand that supply chains are a real thing, whereas before it was not seen. And I think the lessons learned that the auto industry has had and continues to have serious issues with the lithium supply chain or the battery supply chain in general is dawning upon some of these companies which are involved in the hydrogen supply chain. One of the, I guess, from a titanium standpoint, what we have in the titanium industry, which is a bit different than what we've had in the lithium or rare earths industry, is that you've already got large incumbent supply there, and you've got a large amount of titanium metal scrap, which is not 100% recycled today. It's either downcycled into the steel industry or it's lost. So I think we've got feedstock there that we can already secure into the future to meet some of those demands. And we can, working with industry early over the next few years, we can help to bridge that supply gap. Now, if the fuel cells take off as we potentially expect them to, it just means that we need to plan for bringing online our Titan project and manufacturing titanium minerals into titanium metal using our process. So I think with the industry industry in general having learned its lesson because of the pandemic and because of the issues that the battery industry is having today, we are seeing groups reach out, and we feel that with time, given over the next few years, we can do a lot. We can do a lot to bring in a lot of that lost titanium scrap, which is not 100% recycled today. I'll actually bring up a slide just so I know, just so I can note for you. We actually see a lot of scrap that we can...
maybe Tasso, if you could just mention to our group how much scrap comes off of titanium production, because I believe it's a massive amount.
It's 60,000 tons just in the United States today, and it's probably an equivalent amount in Europe today. Now, this is production scrap, a lot of production scrap. This is not just end of life scrap. So you look at that, a lot of that scrap, probably 60% of it is able to be recycled, but a lot of it is not able to be recycled in the current process. We can take that scrap and we can recycle it. So that already is a lot for the next decade of PEM production. When you take into account that annual scrap, and then you take into account that we can form circular supply chains for those PEM electrolyzer manufacturers, where at the end of 7 years, 10 years, that electrolyzer stack is recycled. We can fully recycle all the titanium metal components in there. We can help alleviate, at least in the next decade, by working together with these groups, that titanium shortfall in the green hydrogen economy. So I think that was not the case. You didn't have a large incumbent lithium supply, rare earth supply, which you could build. Now they're trying to build, like Redwood Materials is building the recycling for lithium today, for the cathode today. But they have to wait for that production scrap to be created first. You need to wait for electric vehicles to come out already first. We've got the advantageous position where we're like Redwood Materials. We can fully recycle that titanium metal that comes out of the electrolyzer stack, but we've got the advantageous position of we already have access to a lot of scrap, which we can start recycling and start filling those gaps for the hydrogen economy today.
And Tasso, maybe it would be helpful for our group here if we talked about why you need scrap material, why you need to powderize the material, and what's your technology. I guess maybe if we could delve a little bit into your technology and what exactly it does and how it's different than other technologies that are being used in titanium today in order to develop the titanium necessary for an electrolyzer.
Yeah, so it's a good question. So today there's only one conventional process or commercial process other than ours that we're scaling up to manufacture titanium metal, and that's called the Kroll process. And the issue with titanium metal is similar to the issue that was around for aluminum metal over 100 years ago, where the oxygen bonds, titanium forms a skin of titanium dioxide, very small. Immediately when it interacts with the atmosphere, it forms a 5 nanometer skin of titanium dioxide. Those titanium oxygen bonds are very strong. That's what gives it essentially its corrosion resistance. If you scratch that skin, it immediately forms the titanium dioxide in the scratch. So it doesn't corrode. It does not corrode. Aluminum was the same 150 years ago, and then they figured out that electrolysis could break those bonds and you could create purified aluminum. For titanium, though, electrolysis didn't work. For titanium, traditional reduction processes like a blast furnace, taking iron ore, which is Fe2O3, and put it through a blast furnace, get the carbon out, and then you have molten iron metal. That doesn't work because titanium is too reactive. It will pick up the oxygen immediately. So the traditional process, the Kroll process, was invented where you break those oxygen bonds with a lot of energy. So it's in the first step, you create titanium tetrachloride. You break those bonds by adding a lot of energy in a chlorinator. You hit it with a lot of carbon, so a lot of coke, to create carbon dioxide. So that's why it's so emissions heavy. And then because it's highly energy intensive, and then you hit it with a lot of chlorine. That's why it's quite a toxic process. And you create titanium tetrachloride. Titanium tetrachloride, you put it into a big vat under a vacuum, and you hit it with molten magnesium metal. That molten magnesium metal reacts with titanium tetrachloride, creates purified titanium and magnesium chloride in this big vat. You then heat it over weeks. It's a very long process, very long batch process. Over weeks, you're able to distill out that molten magnesium metal, and you're left with this spongy, coral-like appearance of titanium metal sponge. And then you can take that sponge, but then you have to melt it under a vacuum. You have to go through that complex process. It all came down to not being able to break those oxygen bonds to start with. So what our process does, now I should note that titanium metal scrap becomes scrap that is not able to be recycled because it's picked up too much oxygen. You can imagine swarf or chips or stuff like that. The surface area is large, picks up oxygen. You don't want oxygen on the inside of the metal, it makes it brittle. You just want it on the surface of the metal. So it all comes down to, you couldn't break those bonds. You had to go through this nasty carbon intensive Kroll process. So our process is based on a scientific breakthrough Dr. Fong had in 2016, where he saw that when you add a little bit of hydrogen into the processing of titanium metal, into the refining of it, you actually slightly destabilize those titanium oxygen bonds. And all of a sudden, you don't have to go through that crazy process. You can just use any metallothermic reductant. In this case, we use not molten magnesium, just magnesium powders. And the magnesium powders take the oxygen, create magnesium oxide, and we're left with purified titanium metal, and we can do it in a powder form. Now, from a powder form, what you have advantages of rather than a large ingot is that not only do you have a cheap powder that you're manufacturing from the get-go, you don't have any carbon emissions, but from a powder form, you can go directly into, like we can make spherical or angular powders with some pre-processing. With spherical powders, we can go directly into additive manufacturing processes, which you use a lot of for some of these components, for especially for the porous transport layers. Or you can go into traditional plates or bars or rods. And so you can go into any near net shape titanium component, right? And you can do it in only a few steps. So you want a rod, maybe you sinter it into a rod and you extrude it once or twice, rather than have this huge this very long multi-step complex process. And so you're not just changing the refining or upending the refining of titanium metal, you're also reducing that complexity of the titanium supply chain to get to a part by going directly to powders. And that's because all of a sudden we can deoxygenate titanium. When prior to 2016 and Dr. Fong's scientific breakthrough, you could not directly deoxygenate titanium mineral or titanium scrap with high oxygen content in it. Revolutionizes the way you can refine titanium metal.
Got it. Okay. And so how do you guys, how are you linking yourself to the large titanium producers today, the incumbent producers, to get their scrap metals? How does that relationship work? What's the commercial agreement that you're entering into there? And then, but before we head to more Q&A, I just wanted to let everybody in the audience know, please, if you have questions, I'm sure you do, enter them into the Q&A box or raise your hand, and I can certainly unmute you as well. I think I can, but I will try to unmute you as well, and let you guys speak to Tasso directly, rather than just me asking questions. So I guess, first for me, is the commercial relationship you have.
From the scrap side, it's a good question. So as we're looking at scrap, the current industry is actually quite fractured. So you have different sponge producers. You have some integrated sponge to titanium melted product producers, some that go into some mill products. But typically, we're taking scrap from the point of where it's a mill product that's being made into a titanium metal part or component that's going into either a watch or something like that. So when you look at that, there's quite a lot of different machine shops that will take in a titanium bar, for instance, or take the case of watches, you take in a block of titanium metal, you machine most of that block out to create a titanium metal watch. All that machining chips is typically, in that case, the property of that machine house. And then there is quite a large titanium brokered recycling market across this country, across the United States, across Europe, which takes that scrap and then resells it. Resells the scrap that they can, sends the scrap that they can't resell to the titanium industry into the steel industry as an additive. And so we're able to engage there and get that both, take any of that scrap. There's also the larger machine shops, larger OEMs who are using titanium metal, who have their own machine scrap as well. We engage directly with them. There's some large manufacturers of aerospace components, of medical components, of consumer electronics components, where we can engage directly with them. They have an inventory of scrap that they're generating, some of which they don't know what to do with, or they're downcycling, and we're able to enter the negotiations with those groups. We hardly and have not needed to negotiate with the existing titanium metal mill product producers that are typically selling into the aerospace industry. We're dealing with the machine shops or the end users who want to recycle their products, to work with them to solve their supply chain needs or the circularity of their processes. And I think that's what you're going to also see a lot of with the hydrogen electrolyzers. I think not only us supplying into them virgin titanium or first pass titanium metal, so taking recycled content from, we have, for instance, we know of a lot of titanium metal in a particular operation that never went into operation. It's a nuclear power plant, never went into operation. There's 500 tons of titanium metal there. We could take that, recycle it, send it into the green hydrogen economy. Once it's in with that, with whatever company takes it, we can then set up that continuous circular supply chain. So every time those components come off, we just start recycling them. I think you're going to see a lot of that, not only us securing scrap, but us being the solution provider, similar to what Redwood Materials will be in the electric vehicle industry, the lithium ion industry, very similar to that. We're not only supplying the first pass of titanium metal into their systems, but we're also doing the full recyclability for decades.
The circularity, got it. And then as we think about titanium, maybe a little bit further out, I understand the use case now for aerospace, and I do want to talk a little bit about how you manage the kind of quality control, because that's an area that needs significant quality control. But I'm also interested in kind of, because titanium is so light, the potential uses of titanium in other industries like the auto industry for EVs, where you got huge batteries, as you know, that are very heavy, but you could make you could make the EV a lot lighter using titanium rather than the metals that are used today.
Yeah, absolutely. So there's a range of additional industries. We've obviously got into bikes and micromobility, which is a lot EV related, bikes, scooters, electric bikes. Titanium metal, absolutely. When somebody needs to lift something, it's far lighter, it's far stronger. The strength to weight is way better. Titanium is used in high-end automotive today, and bringing down its cost. Actually, the Department of Energy funded their technology because they wanted cheaper titanium so that it would be used in the vehicle industry in greater numbers or greater tonnages to reduce the weight. So we see it in EVs, in trucks, in marine, where that lightweight is extremely important. So absolutely, and we're having great discussions with a few different groups there. That process of entering the market is, takes some time. There could be some, we believe we're going to have some titanium components from our titanium in the next few years in some vehicles across different brands. But to get a battery pack, maybe it takes a few more years out from that. But absolutely, in the next 5-10 years, for sure. More titanium in marine, more titanium in trucks, more titanium in EVs. There's no doubt about that. It's a premium metal, strong, lightweight, corrosion resistant. It's fantastic. Consumer electronics is also a big one. You have a lot of aluminum and a lot of stainless steel use today. You have limited titanium metal use, but you can imagine as phones or as smart watches or as things like that get smaller, lighter, thinner, aluminum doesn't have the structural integrity. Stainless steel does, but it's heavier. Titanium absolutely does. And titanium is infinitely recyclable, and titanium is lighter. So you have that structural integrity. It can be rolled out across, if it's cheaper and more sustainable, it can be rolled out across many different applications in consumer electronics. You could imagine it's a huge, huge market there. So we see immense markets there, and we see those markets, both consumer electronics, bikes, luxury goods, which is a similar sort of market, automotive, relatively short qualification periods. We produce high quality powders day in, day out. One of our first customers was Panerai, part of the Richemont Group, one of the largest luxury listed groups in Europe, $80 billion market cap. Although luxury goods, if it breaks, it doesn't kill anybody. But when somebody's paying, tens of thousands of dollars for a watch, it can't break. Right. So he can't. So, we have got highest quality titanium metal out. We meet or exceed most of the benchmarks for titanium metal today already. So, and that will only improve as we scale. So we meet it. The thing is that different industries have different qualification processes. When you look at luxury goods, consumer electronics, you're talking 3-6 months, maybe a year, depending on the product, but you're not talking long qualification process, because if it does break in the end, then it's not critical. It's not a catastrophic failure. It doesn't cause a loss of life. Fairly similar with automotive. Maybe you're, a 6 to 12 month process there, and we've been going through it with some automotive customers today. But if you, automotive OEMs today, but if you look at aerospace, that is an industry which we haven't talked a lot about. We're naturally talking to the aerospace industry. We won the US Air Force Research Labs challenge. We're working with US Air Force Research Labs. That's, everybody knows that. We announced that. Working with US NavAir. But commercial aerospace, while we talk to the industry, they do need a wealth of data. They do need that. Our products have been out there in the market for a long time, so the qualification processes are longer in that market. You're talking 3 to 5 years. Will we supply into aerospace in the future? We believe we will. We believe we'll be a big supplier in aerospace in the future. But will it be some of our first customers? I don't think so. Do we work with them? Absolutely. They see the importance of ex-China, ex-Russia supply chain, sustainable supply chain, lower cost. But is it something that we're going to build a business on? Probably not, or no, but it will be a part of our market in the future. But I see markets in consumer electronics, in hydrogen, in bikes, in automotive that are far larger than what the aerospace industry is today. So I think we're in a really, really good spot from a entering the market standpoint. We've already got some customers, but this business we're going to be building for the next few decades, because there's just anywhere where you see stainless steel, anywhere where you see structural metals and you need them to be strong, lightweight, corrosion resistant, our titanium could be used.
Sure. Got it. We have a question that's coming from the audience, but it also links into a question that I was going to ask as well. So the question from the audience is, can you talk more about the financials, your capital needs, and the gross profit potential here? But I guess maybe I'll add to that a little bit. When do you think you're going to be at the inflection point as a company when you'll be margin positive and start to be profitable?
Yeah, it's a good question. So our industrial pilot facility has proven the process out, and we've been working with our partners that are supplying the key equipment into the facility for Virginia, and we've made a lot of headway there, and we're well advanced on our detailed engineering work. But I think when we look at our Virginia facility, although we call it the titanium demonstration facility, it's the demonstration of commercial scale. So we are aiming to be profitable in that facility. Now, we're just finalizing some work around the titanium demonstration facility, and we'll be updating the markets in due course as to updated CapEx and OpEx around there, and our thoughts around when we'll be margin positive. But I would say that in the 2024 timeframe, we're ramping up capacity in Virginia, and we will be aiming to really start generating significant both revenues but also margin. But there's going to be more to come there. And then from there, it's quite a scalable technology, modular as well. So we're very focused on getting to that inflection point in a short space of time. That's unique in new technologies. Typically, like you see in the lithium industry, you look at DLE, for instance. Great technology, needs to work in the long term for lithium, for the growth of lithium. But you're talking you need to build $1 billion plant to prove it out, to make it work, whether it's clays or whether it's that direct lithium extraction. Here we don't. We're talking about 15 to 20 million for our first plant. That will get into us, that we believe we'll be able to hit profitability with that, and then scale from there. And then our scale is modular. That's because this is, although the science is new, it's undiscovered, the process or the mechanical equipment or the furnaces that we need to do it in are not new, they're off the shelf. So we can scale this. It's capital efficient. We can scale it quickly, and it can be extremely capital efficient. And we believe we can move into positive cash flow very quickly. And we don't have the challenges of some of these other technologies, which actually rely on completely new equipment to be manufactured and produced and require large volumes to showcase the economics of it.
Okay, got it. Well, Tasso, I know I told you it'd be 45 minutes. I'm already 7 minutes over my allotted time that you were generous enough to give me. But let me just finish up the call with one kind of key question. What are the milestones we should be thinking about, the targets we should be thinking about for the company for the next 12 to 24 months?
Over the next 12 to 24 months, there's some really key ones. A key one, of course, is us signing more customers. We're in deep discussions with customers across different target markets, and we believe that over the next 6 to 12 months, we'll be signing some really key strategic names, including from the hydrogen economy. And it just showcases the potential for our business. It's similar to when we signed Tesla at Piedmont. It created a lot of value and really put us on the map at Piedmont as a serious lithium producer. I think people already see that we're serious, but I think with some large customers, if we can push those across the line that we're dealing with today, that is going to be an inflection point valuation of our and the development of our company. But then if you look at over 12 months, we're not like some of these other development projects. Again, because we're capital efficient, we've significantly advanced our business. Over the next 12 months, you're looking at us actually scaling up. So actually starting to produce at much scale. And so that naturally is going to be an inflection point, because once you've built 125 tons, there's no reason why you can't build 10 times that or 100 times that in the future. So, so that's a natural inflection point as well. Scaling it up, getting to cash flow, and then continuing to scale up after that. And then, one area which we haven't talked about a lot here is on the Titan project. We have said the next 12 months we expect to be permitted. And if we have a permitted titanium mineral resource that also has the rare earths in it, that's of a lot of value for our company as well. Strategically, we don't need it for a few years out, but just having that project sitting there, that's also got that valuable co-product of rare earths, is a lot of value to our company. But where I see the most value is customers and the scale up in the next 12 months.
Got it. Well, Tasso, this was a fascinating conversation. Thanks so much for your time today. Thanks so much, of course, for the hydrogen aspect of this as well, and the report you guys released late last week. Very extremely interesting, and I think highlights a supply chain issue that's quickly rising, and so the electrolyzer manufacturers should be all over this. But wanted to thank you for your time today, for you give us access to your thinking, and hopefully we'll come back here in 3-6 months and check in on the progress.
Absolutely. I appreciate it, James. Thanks very much.
Thank you, Tasso. All right, take care.